Remember, we do have a test on Wednesday. I'll be reviewing for the first hour Tuesday night before lab. And if it's clear, we are going out. If it's not clear, I'm going to give you time to study. That's what's going down tomorrow night.
I'm sorry. I'm so excited.
Well, I always hope it's clear, just for the record.
It's going to be clear. Just bank on it. It's going to be clear.
I'm hedging, doing what I can to make sure that happens. Juliet asked about the chapters. We've now finished chapter 5, but chapter 5 will not be on the exam. It's just through chapter 4. The reason being, I want you to have time to have the material sunk in. The homework that's due on Wednesday is on chapters 3 and 4. That's, of course, half of the chapters that's on the test. So I would strongly recommend doing that homework before the exam, just to make sure you've gone through homework on the material.
So the exam only is chapter 4?
The exam will be 1, 2, 3, 4.
Okay, so then you
for this class. Remember, physics is 1, 2, 3.
Oh yeah. Wait, but then
as soon as you were like, wait, was this topic like this class or the? I'm like,
wait. So then, you said the homework for this week,
this class,
3 to 4, right?
Yes.
Well, then doesn't that mean that material is technically like on the exam too?
Yes, it is.
Oh.
That's why I say I recommend you do that homework before the exam, because that's covered on the exam.
Okay. I'm glad you clarified, because I thought I read you read an email or something like that. Sorry, I can't speak right now.
Other class.
Was it the one?
Yes. It's trouble with these 3 people in both classes.
I can't.
No,
I can't speak right now. I can't.
Okay. So I've got like 3 slides of additional material from what we talked about chapter 5 on Friday. And then we'll go into chapter 6, talking about telescopes. So I mentioned Kirchhoff's laws about the 3 ways of observing a star. So you have the continuous spectrum. What geometry do you need to see the continuous spectrum from a star? What geometry did you need to see the continuous spectrum from a star?
Oh, is there like there's no other gases in front of it?
Right, no gas in front. If you're looking directly at the star with no gases between you. So if you have a star here, and your eyeball is right here, and there's nothing between you, then you're going to see that continuous spectrum. Then we have the emission spectrum. Do you remember what geometry gives us the emission spectrum, where you see the emission lines from gas?
like it's going through a gas cloud thing before reaching you.
That's actually the absorption spectrum. But you have to have the gas cloud, and if your eyeball is like that.
Backwards. Okay.
So this one here sees the emission spectrum. Why is it the emission spectrum? Because you are not looking at this continuous source.
Right. I was thinking never mind.
And so the last question, the absorption spectrum, is the answer you gave, but now I think you understand clearly. If you're looking like this, you have the continuous spectrum with the cloud in between. The cloud is absorbing, and so you have the absorption spectrum.
So I'm having issues with those 2, all right? Yeah, how do you, is the cloud always going to look like that? Like, how do you know where you're looking? Like, I guess I'm not understanding the picture.
Okay, so to make this I'm trying to make it as clear to observers or to think about as possible. When light goes through the cloud, you're going to have atoms in the cloud have electrons that absorb just the right energies, and so you absorb some energy. So if you're looking through the cloud at the source, you're going to see the light from the source with some lines missing that have just the right energies.
Is that the emission?
No, that's the absorption, because it has missing lines. Absorption.
Wait, it has missing lines because of the electrons?
Because the gas absorb the electrons and the molecules absorb only certain energies. Because remember, the electrons can absorb energies if the energy is equal to the energy difference between 2 allowed energy states. And so there's only very specific energies. And so if there's a cloud gas and a light source on the other side, I'll see the light with those absorption lines missing.
Okay. And then,
But if I view it from another angle, so I'm not looking at the source, of course I'm not going to see the continuous spectrum if I'm not looking at it. But I will then see the electrons fall down and give off the exact same spectrum as they absorb. But the difference is the emission spectrum is going in all directions. So if I'm looking at some angle where I'm not looking at the source, I'll see the emitted light, and that's all I'll see.
so if you're not looking at the source, isn't like the light?
Yes, that's the light.
Okay.
If I'm looking through the cloud, I do have that emission, but it's really weak compared to the absorption, because the absorption is absorbing light coming this direction. The emission is then going all directions. So that's how we get those three different types of spectra, all from the same original object. I'm actually loving using the pen to go forward, in case you guys wonder. Now, we looked at the sun's spectrum in a very high detailed picture. Remember, it took pretty much the whole page, and it had the lines one after another, so you can see all the detail. This here is actually what scientists look at. They look at a graph like the one on the right, where they see absorption, and, well, you would see a nice smooth line like this normally, and anything that's not following that is absorption. So you tend to think that only this is absorbed. But actually, all of these little wiggles are absorption lines. So there's tons of absorption lines there present. And looking at it like this, you can see how strong they are. Whereas when you're looking, it just looks black and white when you look at the colors, right? If you look at, I don't remember how to do it. Sometimes there's a little magnifier, sometimes there's not. Let's not try to zoom in. Is it there? Yeah. And look, now disappear. Okay, forget it. I was going to zoom in, but you can't tell how strong the absorption line is by looking at this. But here you can tell. And here you can see all of the details. You can see, look, there's two there. And there's, all of these. This here has a little two peaks on it. This here definitely has two peaks a little further away. And so astronomers analyze this kind of Whoa. Now what did I do? That's a new one to me. I think that was just slowness of response. Anyway, that's the kind of thing that astronomers are actually analyzing. And from that, they can tell you the composition of the sun's atmosphere. Not the composition in the center of the sun. The composition of the sun's atmosphere. And so here you have it. It is 71.1% by mass hydrogen. Or 91.1%, notice it's got a few more decimal places, by number of atoms, hydrogen. So the sun is largely hydrogen. Usually we just count atoms. 91% hydrogen by atoms. A lot of hydrogen. And then helium is almost 9% of the sun. 91 and 9, of course, adds up to 100. So the sun's atmosphere is virtually all hydrogen and helium. Now, we're going to come back and learn more about this later, but that's an interesting observation. Remember, with the scientific method, you start off with an interesting observation. You say, why? Why is the sun mostly hydrogen, and between hydrogen and helium, virtually 100%? That deserves some kind of hypothesis, which there are plenty, and there's one that's accepted. Other things, carbon, nitrogen, oxygen, neon, and so on. You see, you get down here, and there's very, very little gold and uranium in the atmosphere of the sun. Very, very little. But, there's also a very small amount of iron. So, how do we get that information?
By looking at
The absorption lines in the atmosphere. Now, I talked about the Doppler effect, and I said I should have had the equation, but I didn't. So here, I didn't want to say it because I was worried that I might remember wrong. Fortunately, I would have remembered right, but it's still good to have double check first. So that's the equation for the relative, or the Doppler shift, not relativistic, the Doppler shift for light. For sound, it's a different equation. So the three of you in physics, when we get to this part at the very end of the semester, you'll learn a different equation because we'll learn the equation for sound. Then second semester, we'll see the equation for light, the one you're seeing here. Now, what this says is, what is this symbol? What's the name of that symbol? Lambda. It's the Greek lowercase l. And what does lambda stand for? The wavelength. So the change in wavelength divided by lambda sub 0. It's important to understand what these things are, or else you're just looking at some crazy Greek Greek letters. Delta means change in. That means the difference between two values. Lambda sub 0 is the wavelength that you have if you just have the atoms in the lab. The atoms in the lab. So like when we had the tube with gas in it, lambda 0 would be the wavelength of the absorption or emission line. We were looking at emission lines here, so the wavelength at emission line. Delta lambda is the difference between the emission line you would get measured here on Earth, lambda 0, and what you see from a star. So we call that delta lambda over lambda. We call that the redshift, and we give it a variable z. So z is the redshift. Why do we call it the redshift, you ask? Because almost every single object we see out there has a redshift. The number of things with a blue shift are very, very small. It's a very rare thing to have a blue shift. What did a blue shift mean? Don't remember? A blue shift was a shift to higher frequencies. And that occurred if something was moving toward you. See in the picture there. If it's moving toward you, you have a blue shift. Red shift is something moving away. What do scientists believe is happening with our universe? Well, I haven't talked about this, by the way. This is asking for your prior knowledge. They believe it's expanding. So if it's expanding, everything should be moving away from you. Hence, you should have everything redshifted. Now, that's a relatively recent understanding. If you were to go back even, well, it was about 50 to 60 years ago when this idea became predominant. So if you go back 100 years and you said that the universe is expanding, people would have said, you're nuts. They thought that it was pretty much just stationary. That fits very well with the previous models. Remember the model of Aristotle with the crystal spheres and all the stars are out there on the crystal sphere? And the belief that most creationists have held historically is that God created a static universe, that the universe is just going to stay the same. And then scientists are saying, no, everything's moving. Now, we have good observational evidence to say that things are moving. Good observational evidence, not just in the redshifts, right? A lot of people say, we don't understand the redshift quite right. There's a quantum redshift, and that's going to change things a little, and we may be misinterpreting. But we also have what we call the proper motion. We can see in 10 years, the right ascension for this star has shifted by 0.001 arc seconds. Really small angles. You've got to be really precise. But we can actually see them shift, which means, yeah, they're moving. Now, moving this way doesn't mean they're moving away from us, but if they're moving relative to that permanent crystalline sphere, that should be enough to say, yeah, they're not fixed and stationary.
Wait, so the blue shift.
Mm-hmm.
So if we look at like a meteorite falling down, would that be an example?
It would be. The meteor, I don't know.
But would the change be so?
The light that you see from the meteor is not light coming from the moving object. It's light from the atmosphere, which is not moving with respect to you very much. So I don't think that you would see much with the meteor. If you actually were seeing the object, you might see some. When we really see a significant redshift is when we look at something that's moving at a relativistic speed with respect to us. Relativistic means like 10th the speed of light or faster. And you're not going to see much redshift at all if it's not going that fast. Now, if you look at this here is what I was just starting on. This is the speed at which the object's moving. This is the speed of light. If it's moving at 1% the speed of light, you'd have a 1% shift. That's pretty small. The 1% the speed of light is really fast. And so meteorites are coming in very high speed, but not that fast. So here is an example of the shift. So this is the same spectrum. This one, of course, is emission. This one's absorption. And you have something that's moving at 70% or 0.7% the speed of light. So that's not a very big shift. You look here and you see this here has a reasonable shift that you can see on this spectrum here. So you can measure it, but it's not very big. And if it's going faster, it's going to be bigger. And of course, if it's going slower, like it's going 1/10,000th the speed of light, that's really whipping, but you're not going to see anything at all. Okay. Kinds of things that are measured with the Doppler shift. We actually can measure rotation. We can measure the Doppler shift. Now, this takes very sensitive instruments, but you can measure the Doppler shift of something rotating. You see this gas is coming toward you, this gas is going away from you. And so there's a different speed. And so you can take the average Doppler shift and then the shift from one side and the other side. What you're going to see if you look at the shift from that is a widening of the lines because of the rotation. And so they can determine rotational rates by looking at that. Binary stars or stars that are orbiting together. Something that's very cool. You might remember I pointed out the stars in the Big Dipper, and in the handle you had Mizar. And if you look at Mizar in the telescope, you can see that it's not one star, but two stars. Two stars that are orbiting each other. And then if you look with the spectrometer, you see that each one of those two stars has spectra from two stars moving independently. So each one of those two stars in Mizar are actually two stars going around each other. So what we see as one object in the sky with our eyes, Mizar, is actually four stars doing a very complicated little dance around each other. And so it's called a double-double. So the motion of stars in a binary system can be seen by looking at their Doppler shifts. In motion around the sun, if you're the kind of person who believes, that the Earth is moving around the sun, then I'm making the flat earthers a big thing today, or this year. And science can be used for bad as well as good. So this last one here is, police radar uses this effect as well. When you see the fuzz out there with the radar gun, what they're doing is they're sending out an electromagnetic wave. And that electromagnetic wave is reflecting off things and coming back. And then they have their little superheterodyne that is taking the frequency they sent out and the frequency they received, mixing them together and determining the difference in frequency between the two. And from that difference in frequency, using that Doppler shift equation, using this equation right here, to calculate how fast your car is going. I told you, if you use for evil, you gotta be good with nice sciences. It's good, but it's also got some downsides. Now we're going to talk about telescopes. I just think this is a funny cartoon. It's somewhere between a nova and a supernova. Probably a really good nova. Now, a nova means new. So nova is a new star. So Tycho saw his nova, his new star. That's what made him famous. Supernovas are bright. They're a different kind of nova, and they're completely different, it turns out. Supernovae are deaths of really massive stars. Our sun is too small. It will never have a supernova. A nova is a star that's already died that has a companion that has gas that is slipping over to the dead star. And if you get enough gas on the surface, and all of a sudden it undergoes a rapid explosion, and that's what nova is. So they're completely different, but it's fun. Yes.
So, what did you say a supernova was?
A supernova is the final collapse of a supermassive star when it dies.
Okay, but it has to be like a massive star.
It has to be at least 4 solar masses,
Okay.
3 to 4 solar masses.
But if a star collapses and it's not one of those, then it's a nova? Or
No,
No.
it's not. A nova occurs completely different thing. It's not at death like a supernova. A nova occurs when you have a star that's already died. So something like our sun that's already died, so it becomes a white dwarf. If it has a companion star, so if it's part of a binary system, and it has a companion star, and that companion star is dying, during the death stages, the stars blow off a lot of gas. And so if the companion star is blowing off a lot of gas, the dead star will start collecting it. And if it gets enough gas on the surface, it'll suddenly have a fusion event. Basically, a nuclear bomb goes off on the surface. And that's a nova.
okay.
So, we use telescopes. I like this. Telescopes have been used for hundreds of years. When was the first telescope used to observe the sky? Or let's just say, by whom? Galileo, right? So, going back to Galileo's time, telescopes have been used to observe the sky. Back in Galileo's time, you got the telescope, you put your eye to it, and you looked up there, right? That's not what's done anymore. Astronomers who use telescopes for their data collection don't even have to be the same state as their telescope. It's all, we were having a discussion today with the pre-med, well, with the person from Lone Medical School, about doing science laboratories for online courses. And, how do you do a laboratory? And I'm thinking, well, the point of the laboratory is for students to see that what we tell them in class is what really happens. Right? To have that hands-on experience to see, yeah, that's what's going on. Well, with astronomy, everything could be done with online labs. Because the telescope that they use today doesn't even take photographs using normal film. Normal film has a sensitivity, it'll collect about 10% of the light that hits it. Instead of using normal film today, you have a telescope and you have a camera, and that camera uses what's called a charge coupled device, which is on the next slide. I should point out the middle thing. The human eye is just not very sensitive to dim light. Now, our eye is pretty miraculous. We can see a range of about 10 to the 12th in intensity. That's from the dimmest we can see to the brightest we can see before we start blinding ourselves. It's a huge dynamic range. The eye is pretty amazing, but it's not super efficient at low light conditions. And the film is 10% efficient. The CCD, the charge coupled device, is about 75%. Anybody know where you might find a CCD? On the back of your telescope, yes. Or, I was going to say I left mine in my office, but no, I got one right here. This camera here, it has a little really cheesy, cheap lens. And behind that cheesy, cheap lens, can I say cheesy, cheap lens? You buy your cell phones, they're putting more and more research into making better and better lenses to get you better pictures. But behind that, you have a charge coupled device, the CCD. And that CCD is measuring your picture. So if you have a cell phone or a computer with a camera, it has the CCD there. Anything that's taking a digital picture, CCD. And so the telescopes we use have these CCDs that will take a digital picture. And the digital pictures have a lot of real big advantages. For instance, if you have low light conditions, well, with the normal camera, you use a longer exposure. And you hope you got it right. And if you didn't, well, you take another picture. With the CCD, you can just keep going. Oh, that's not enough. Well, let's just continue on. And so with the CCD, you can make your exposure as long as necessary. You can kind of monitor and say, yeah, that's long enough. So you can see really faint things. Now, another thing about the eyeball. The eyeball, we see color, or most of us see colors. Is anyone here black or black? Is anyone here colorblind? I'm only looking at the 3 guys, by the way. It's a sex-linked trait, and it's virtually non-existent within women. There's also people who have super color vision. Oh man, I can't remember what they call it now. And that's exclusively women. Women just have an advantage over men in this color vision thing. So we see things in color, except in low light conditions. I used to keep a nice big 7-Eleven big gold cup next to my bed filled with water. So I wake up in the middle of the night and get a drink of water. Except for the middle of the night, it looks gray and white. Why would it look gray and white when in daytime it looks red and white? You guys are all sleepy as could be, aren't you? It's not even a 1 o'clock class. I took a few when I was in college, and I did snooze a lot. You can't see the red and white in the middle of the night because you don't have color vision in low light conditions. The rods, the things that give you black and white vision, those are much more sensitive than the cones that give you color vision. And so in low light conditions, you can't see colors. So when you look at stars, you usually just see 1,000 points of light. Poor George Bush. Some stars you can see a color to. Those have to be really bright for you to see a color to them. Because only bright light, only light bright compared to stars will allow you to see color. Yeah.
This is the same thing with Venus. Like when we look at it through the sky, that you can typically see like the red color.
Mars.
Sorry, Mars. Man, I am tired today. Oh my gosh, I'm saying Mars. Sorry.
Yeah. With Mars, you can see that it has a red hue with your naked eye. And we'll see like Betelgeuse. You can see Betelgeuse has a reddish hue, and Rigel has a bluish hue.
So it's the same.
But most stars you can't.
It's the same concept with the color.
That's it. It's exactly that. Yeah. Now it's not the Doppler shift. It's how hot they are. Okay, so the CCD collects about 75% of light, and they'll use filters so you can get color vision with your CCD. Obviously, your smartphone has a color camera. And so it's really revolutionized astronomy. You can transmit the pictures over the internet. So you've got a telescope up in Hawaii or in Chile, and you can be at your laboratory in Nebraska, laboratory being your computer's set up in the basement of your house for all anyone cares, and you can see the live pictures, you do all your analysis. You don't have to go out there with a telescope. So the telescopes have operators who maintain them and make sure they're running, and then you have the researchers who control the telescopes remotely. So do you guys know Elena Cornwell? She's the new office manager for humanities. Yeah. Well, her dad used to do that. I had him come do a lecture a few years back when she was taking this class. He was one of the people who worked maintaining the telescopes in Hawaii. So he was one of the people who was actually there, who got to freeze buns in the telescope building because they put them up at high elevations. High elevations because there's less air between you and getting out of the earth. Less air means less things to cause problems with your pictures. But at those high altitudes, it tends to be cold. All right, moving forward. Pictures, pictures, pictures. This picture here, falls color. The colors are indicating motion. The picture on the right also falls color. The one on the right is, actually they might both be x-rays now that I think about it. Actually no, the one on the left is radio, the one on the right is x-rays. So these are the kinds of pictures you might see when you're doing astronomy. This one on the left is really cool. You have your star in the center. Or your former star or your galaxy. I don't remember what this is, so I can't be really, I should know, I think, but that's your object. And this here is jets of gas leaving it. And those jets of gas when they hit other gas are causing shock wave and all of the light that's shown there. So talk about the Crab Nebula. 1054, what's CE mean? Common era. That means after the birth of Christ. AD, what we usually call it. So 1054 AD, astronomers in China saw a guest star. Essentially the same thing that Tycho Brahe saw much later. But Europeans were not communicating effectively with the Asians. And so the Chinese astronomers saw and recorded this, and Europeans weren't really aware of it. So 700 years later, John Beavis, not to be confused with his partner, Bob Butthead, you guys probably too, TV show.
No.
Yeah. So British physician, not physicist, physician, an amateur astronomer noticed with his telescope a faint dim patch of light in the constellation Taurus. And it was named the Crab Nebula, and people noticed, hey, that's the same location where the Chinese astronomers had recorded their guest star. And so it's now become one of the most studied things in the sky. They study it with all different wavelengths so that they can learn more and more about what happened here. What happened here roughly 1,000 years ago? Now, I said roughly 1,000 years ago. Where's the flaw in my statement? What are we doing when we're looking through a telescope? We're seeing. I didn't hear you.
You're looking back.
Yeah, we're looking back in time. We're looking at light that arrived here roughly 1,000 years ago versus light that arrived today. But then you have to take into account how far away is that object and add that to the time as well. But we tend to use the Earth's clock and say this just happened as far as we can see, even if it really happened in reality a long time ago. And so we have a lot of understanding about the death stage by looking. Here's a picture from our textbook, that one was from a previous, looking at Orion. And so you have Orion. This star here is the one I mentioned, Betelgeuse. This one here is Rigel. And if you look with the naked eye, you can see that Betelgeuse has a slightly orangish color and Rigel has a slightly bluish color. Like I said, that's actually telling us about the colors. What color did you have when something was hot? Blue. And when it's cool? Yellow or orange. So Betelgeuse is a red giant. Red because it's relatively cool. Rigel is a bright supergiant or something like that. It's really hot and giant. Both are giving off lots of light. Now, if you look at this, this is visible spectrum in the first picture. The second picture is X-ray. And in the X-ray, you see different details, don't you? It doesn't look like the same picture. And then this third one is infrared. Now let's look at the infrared. In the infrared, what stands out? This thing here is major in infrared. You can see something there. That's the dagger. That region is a region of star formation right now. Well, right now, again, we're getting the light from star formation right now. And so that's one of the really interesting things to observe in astronomy. It is a nursery for stars. Stars are being born there as we watch. See lots of other light all over the place in infrared. You're seeing gas there. So now some telescopes. Here's the Twin Keck telescope. It's binocular vision. I believe this is the Keck Observatory. It actually would say it says down the bottom, large binocular telescope observatory. I thought it was the Keck, but I might be wrong. I've got to hide this just so I can read that. It just says for COSI. Yeah, it doesn't say Keck there. So I might be wrong. That might not be the Keck. But that's got binocular vision, 2 telescopes. Why 2? Did you say 2 is better than 1? Good answer, good answer. Well, with 2, there's a couple things you have going on. One is that you have a certain amount of binocular vision that you can triangulate. But another one that's really important is you can actually take the picture you get from one telescope and the picture you get from the other one, and you can combine the information from those 2, and you can get much sharper resolution. As you can see, a lot finer detail. And so that's a way of getting better detail for those telescopes. Uh-oh. I have no idea why that happened. It wasn't supposed to, that's for sure. This program wasn't even open. This here is kind of famous, the Arecibo telescope. How many people have seen pictures of this telescope? Anybody seen the movie Goldeneye? Yeah, seen Goldeneye, right? There's a lot of bad physics, by the way, involving this in Goldeneye. Things like, for instance, how is it hidden in the movie Goldeneye? The telescope is hidden. Nobody's supposed to know it's there. Because they have it flooded with water, remember? And then they drain it. And the really crazy thing is it drains and it gets close to the bottom. First of all, you notice as it drains, the walls are dry, but like a foot above the water. So as the water goes down, it's drying instantly. Then when it gets down to the very bottom, I kid you not, you see the water jump up and go down the drain. This is something that physics will learn about, not so much here. But there's this thing we call the second law of thermodynamics. And that's a violation of the second law of thermodynamics. It's not going to happen. You know from watching the movie that what they did is they filled a model, of course, they didn't use the actual telescope. They filled the model up and then they just played the video in reverse. And they didn't worry about what was happening at the end. Yeah. But anyway, that's not relevant to us. I'm sorry. This is a huge telescope. By the way, every time I use this, I think about that movie because remember the guy's like, click, click, click on this pin. I'm invincible. And then he's got the pin that has the bomb in it, and when you click it 3 times, it blows up and he dies. Yeah. Anyways, that's what I think about when I do this. This telescope is huge. 305 meters across. Just to give you a feel, a football field from end zone to end zone. That is not from inside the end zone, but back in the end zone to back in the end zone. It's about 100 meters. So that's like 3 football fields across. That's a pretty big telescope. It takes up 118 acres. We got 40 acres of almonds back home. We feel that's pretty big. 118 acres. Huge. So why would it be so big? There are actually 2 reasons, neither of which we've talked about. So I'm just asking you to, you observe something interesting, you make a hypothesis. Why do you think it's so big?
The telescope?
Yeah.
Collect more
Collect more what?
data.
More data. What does that mean to say collect more data?
So take more pictures. Bigger area.
Okay, he's on the right track.
Bigger range of area that they can see through the telescope. I don't know.
It doesn't change that. What it changes is how much light you collect. Think of it, we often talk about telescopes as light buckets. The idea being it's raining. And if you put out a little bucket, you're not going to get much water in that bucket. Put out a big bucket, you're going to get a lot more water. Well, you have light that's coming from the sky in the same matter as rain. manner of this ring. And so if you have a big telescope, you can collect more light. The more light you collect, the fainter the objects are you can see. So one reason it's so big is to collect a lot more radiation. It's a radio telescope. The strength of the radio waves we receive is really weak. So making it really big allows you to see much fainter things. There's a second aspect that you wouldn't have guessed. The bigger the telescope, the finer the detail you can see. Now, unfortunately, the detail you can see is also proportional to the wavelength. Radio waves are on the very large wavelength side of the spectrum. Radio waves are measured in like centimeters, whereas light waves are measured in nanometers. There's a difference of about 1 million times in the wavelength of radio waves compared to visible light, which means the detail you can see is about 1 million times smaller with visible light than you can see with a radio telescope. So even making a telescope huge like this, you still don't have good resolution. They can improve that. Like I said, the binocular telescope makes it so you get resolution that's better. If you take a second telescope and you have it far away, like orbiting the Earth, and then you use interferometry, you take the two images and combine them, then you can get much better resolution. And it's not even on the Earth. One on the Earth and one orbiting the Earth to get good resolution. Visible telescopes. This one here, small opening, collects less light, so you only see the very brightest stars. This one here, bigger opening, collects more light, you can see fainter stars. So if you look at the pictures, you see that you have the same stars here as you have here, plus there's more here. And the stars are bigger in this picture because they're going to appear brighter.
So the bigger the telescope, the more light you can...
Yep. And in fact, we have this important equation. The collecting area, the light gathering power, you'll see an equation on the test form for LGP, not this test. Light gathering power is equal to the area, which is pi over 4 times the diameter squared. That's just the equation for the area of the circle. Pi r squared, or pi times diameter squared divided by 4. So if you're buying a telescope, that's the first important thing to look for. Buy the biggest diameter telescope you can afford, because that's going to allow you to see the faintest things, which is the coolest things. Also, it gives you the best resolution. So 2 good reasons. Bigger is better. Spend your money first for the biggest telescope you can afford, and do make sure it has quality optics. Because poor optics, of course, if they just put window glass in there, it's never going to do you any good. So high quality optics and as big as possible. One of the interesting things that astronomers do is they filter light. I was a bad person. When I was teaching at PUC, we had the telescope open every Friday night, so people would go to Vespers and after Vespers, go up to the telescope and we point out some things in the sky. So for fun one night, I put in a red filter and looked at Mars. And wow, it's really red. Yeah. That's just, it's really bad, right? You're misleading the public. Then I'm laughing, saying, no, it's not, but The filters are used to see different features. And so you can see here a U for UV filter, B for blue, V for, what does V stand for? I'm looking at you, Leslie. What does V stand for?
I don't want to be wrong.
You'll be right.
No.
Look at the picture. Use the reason I picked on Leslie and not anyone else in this room. What would V stand for?
Velocity? I don't know.
What color is the V?
Violet? I don't know. Oh, I can't see it.
It's green. Yeah, it'd be for Verde or something like that.
Oh, sorry, I can't.
It's the green filter is V.
Oh, I had no idea it was going to be Spanish.
Yeah.
I'm sorry.
R for that's why I picked you. I figured you would be the one who would go for it.
I didn't know what it was talking about.
Yeah. Okay, red for rojo, obviously.
Oh, okay.
Uh-oh. Good. R for red. Um,
It's like, what?
yeah, I'm good at this English language thing. Maybe I should go to Spanish, which I don't speak. I for infrared. So those different filters allow you to see different details. They're not coloring the light. They're taking away light. They're taking away all the light that's not the color of the filter.
But why did they use B instead of G?
Honestly, I don't know. I wondered that myself. Especially since V could be thought of as violet.
Yeah, so I was like, wait, what are you talking about?
Okay, so that allows them to look at particular wavelengths, and then they can get more specific information about certain things. Now, a little physics. This here, I'm not going to hold you to knowing this on the test. It's just background so you can understand what a lens does. So lenses aren't magic. So refraction is bending of light when it goes from a material with one speed into a material with another speed. And it's just like when you ride your bicycle on the beach. So you're riding your bicycle on the concrete sidewalk, you're cruising right along. If you go onto the sand, what happens? You fall. Well, let's assume that you don't fall.
It's hard. You say right on the sand.
Yeah.
It's really hard.
It's hard, right? It slows you way down. And what naturally happens if you turn off because of the slowing, if you don't fall, what you do end up doing is turning violently. Because your front end basically stops while your rear end is going nicely. It pushes you sideways. Well, that's what happens with waves, with light, with sound. When you go into something with a slower speed, the direction that it's traveling will bend toward what we call the normal. So the normal direction is the direction that is perpendicular to the surface. So the normal, well, that's not perfect. That's the same as I drew before. That's pretty good. Except for now I see that color just doesn't stand out. Going super slow. Okay, that's the normal direction to the best of my drawing. And so when you go from air into glass, the light travels more slowly in glass. Hence, it bends toward that normal when it goes into glass. If you go the opposite direction, light works the same forward and backward. So if you go from glass into air, it'll bend away from the normal. Good.
I was thinking it recurves itself then by coming back up.
Yes, so if you have a glass plane, glass that's parallel on both sides, the light coming in will change direction in the glass. If you have two parallel planes, and I'm illustrating that mirror is correct if anyone wants to know what I'm doing here. There's the light coming in. It goes like this through it, and then it comes like this, so it's going parallel to its original direction. So yes, the idea of it corrects itself.
Wait, it does that because of similar to what you mentioned. It's like it's harder. It's like when you're riding a bike on the sand.
Yes, when it goes into the glass, it goes slower in the glass. It's harder to go through. It has an impediment, and so that makes it bend toward the normal. When it comes out, it goes freely. It bends away from the normal. So that allows us to make lenses. Lenses are things that have a curvature. So if light goes into the top, it's going to bend down to go toward the normal. If it goes in the bottom, it's going to bend up to go toward the normal. So you put that together. Let's get past this. Get past this. Put that together, and it makes light that was initially parallel. These two rays are parallel. Makes it come together and meet at a spot. We call that a focus when it comes together. And so you can focus light with a lens because of this refraction. Refraction telescopes, they're the kind that you often get for your home. They're not used in research anymore. This is, I think, the Yerkes telescope, the largest refractor, the largest lens-based telescope in the world. What is it? Something like 1 meter for its objective. Yeah, it says up there 1 meter. The lens is 1 meter for the objective. 1 meter. It has a lens this big. What could go wrong having a lens this big? It's what? It's so heavy that it deforms under its own weight. Furthermore, you have there's all kinds of problems with them. And so you see here the glass sags under its own weight, defocusing the light. You have chromatic aberration. As different colors actually focus differently because the speed of light varies with color. We saw that, we saw pictures with the prism. That's why in getting to this, we had the picture with the prism. Because different colors bend different amounts, refract different amounts. So you have what's called chromatic aberration, an aberration or error in the image due to different colors, chroma. So instead we use reflectors. And I'll start with reflectors on Friday. Reminder, tomorrow night I'll be reviewing for the exam.